Hello, welcome to my first video in the series of Mr. H's Cram notes, and I'm going to begin by talking about the von Neumann computer model. Now, you probably will never get asked to draw any of these diagrams, but it's actually quite amazing how well you can explain things by using this very simple model if you understand and have a conceptual idea, if you have this model sort of squared away in your head. And so we're going to begin looking at an overview of a great chunk of the syllabus using this model. Right, okay, this has turned into a bit of a thing. Right, so here's our basic von Neumann computer model, and as you can see we have inputs, a processor, and output, and storage or memory. Now, probably seen this many times before, but there's a couple of things I want to point out and I want you to take particular note of. The first one is that this primary storage or memory is responsible for storing both data and instructions. Also notice that for the processor to execute any instructions, it has to load them from this memory store. If it has to process any data, it has to load it from the memory store. The other important thing to note is that there's only one bus connecting that processor to the memory store, and this is known as the von Neumann bottleneck. It's known as the von Neumann bottleneck because it doesn't matter whether the processor wants data or instructions, there's still only one bus to move that data or instructions to the processor. Another key topic throughout the entire syllabus is understanding that in the real world, most of the data that comes in the form of an analog signal. Likewise, because we want to send information back out to people, we have to make use of analog signals as well. Computers, on the other hand, all this bit in the middle, the processing and the storage of the data, all takes place as digital, which is, in other words, another way of saying that all the processing of all the information that happens inside a computer, the CPU, the processor, and all the storage that goes on, all that information is digitized, all represented as binary ones and zeros. And so an entire section from paper 2 is devoted to how do we represent different types of data in binary format. And the reason for that being so important is because if the CPU is going to process it, or if primary memory is going to, or secondary memory is going to store it, it has to convert it to digital binary ones and zeros representing on and off states in our computer model. Right, in this slide, what's happened is we have very slightly we've refined that original block that we simply called memory storage into two different parts. The first part is known as primary memory because it's first, and it is the part that the processor first accesses. Now, primary memory is also known as RAM, which stands for random access memory. And primary memory, the important thing is it works on electricity, which means it's volatile. In other words, no power, no memory. An entire section 1.2 is devoted to different memory technologies. Secondary storage, on the other hand, is non-volatile, and it makes use of a number of other technologies, and this is where we save things for more long term. And the section 1.3 of the syllabus deals with understanding all the technologies that go into secondary storage. The next video in this series we will deal with the CPU, which is section 1.1, where we deal with the CPU and caching. And just to iterate, the CPU has a number of main subcomponents. These are, you can think about them as being like the parts of an atom or part of the cell, and the subcomponents of the CPU are the A or the U, arithmetic logic unit, the CU, the control unit, registers, and the cache. Getting down briefly into the difference between different memory types. Secondary storage, the three main technologies that exist today are magnetic storage, optical storage, which is like meaning using light, and solid state. Now, primary memory, remember, is volatile, and it makes use typically of a technology known as DRAM or dynamic RAM. The problem with dynamic RAM is that it requires refresh cycles to continuously update the memory cells, because it's built on the same technology that goes into making capacitors. Now, this memory is rather inexpensive, but not as efficient as we would like. So a far more expensive type of memory, called SRAM, standing for static RAM, which is built on transistors arranged in a certain configuration, which requires no refresh cycles. It still requires electricity, but there are no refresh cycles. Now, the problem with primary memory's refresh cycles in DRAM is that whenever one of those refresh cycles is happening, the processor has to wait, and it cannot read or write to or from primary memory. So no data or instructions can be loaded or accessed from primary memory during one of the refresh cycles. And this is the reason that cache has been introduced. It's much smaller but more expensive than primary memory, but a heck of a lot faster, for no other reason other than the fact that there are no refresh cycles, and therefore the CPU, the processor, doesn't have to wait for the memory to finish doing one of its refresh cycles. Another thing to be reminded of is that even though cache is considerably faster than primary memory, relatively speaking, secondary storage is incredibly slow. Now, one of the issues that you run into is that obviously RAM, being relatively expensive in terms of how many of its cost per megabyte compared to secondary storage, means you don't have an awful lot of it. It's far more finite than the amount of storage we have in secondary storage, and that's managing of sometimes using secondary storage, even though it's slower, to swap out bits of memory from primary memory when we run out of space to the secondary storage is known as virtual memory, and that's a very important consideration, and we'll talk about that in one of the subsequent sections. The other thing which you may or may not have thought about is what happens when the computer boots up. Now, I've already said all the instructions that the CPU executes must be loaded into primary memory. But how is that going to happen when the computer is off and then started up? Because remember, RAM is volatile, so the minute I power the computer down, the instructions in primary memory will be lost. You probably think, well, it just loads it from the disk, but that's not entirely true. You cannot simply load things from the disk, because at this point the computer system does not know how to talk to the hard disk or even load a file, or even what a file is for that matter. So to this end, the CPU is hardwired when it boots up or starts up to go to another type of non-volatile memory known as the ROM BIOS. ROM stands for read-only memory, and BIOS stands for basic input-output system. And it's this ROM BIOS that then in turn is loaded in primary memory and runs a certain few instructions, which ultimately runs and pulls a bootloader from the secondary storage, and then ultimately loads the operating system. We deal with the operating system and system software in section 1.3 of this course. There are different levels of cache. Level 1 is within the CPU itself. Level 2 nowadays is also on the CPU, whereas level 3 typically is not. The lower the cache level number, the smaller the cache, but also the more efficient it is. Finally, I'd like to point out that the modern computer has more than one core. However, this technology would not be possible without cache. Let's think about why. If we had no cache memory, we'd be back at the situation where we just simply had this as our model. If I had multiple cores in this model, let's suppose I had a call there and a call there. Regardless of whether core 1 or core 2 wanted to execute an instruction, the one would still have to wait for the other, because there's still only one channel to move the information through. Namely, we still have the von Neumann bottleneck. However, the cache memory, things are much faster. Each core would have its own level 1 and level 2 cache, and as long as it had the data that it needed loaded into its level 1 and level 2 cache, that core can continue operating independently of having to wait for much slower static RAM. As and when a core requires data from primary memory, there's usually enough information and data for the other core to still keep processing with whatever it has in its cache. If it doesn't have what it needs in its cache, it will then just have to wait. But in most cases, there's normally enough data for it to get on and do something else with out of order instruction execution and so on and so forth. So thanks for watching. So I hope this has given you a good overview of the syllabus as a whole, and I hope you've got this model, as simple as it is, squared away nice and tightly in your mind, and remember it when we talk about all the sections of this course. Mr. Holmes signing out.